4 discusses oscillations. In this lab, we examined the motion of a spring mass system in which the mass swung in an arc while oscillating on the spring. We extracted position versus time data in both the x and y directions using Tracker, then we wrote a program in GlowScript that we then compared to the experimental model. In addition to this, we modeled the change in energy throughout the system using our GlowScript code. The concepts used in this lab. Just like in previous labs, Newton's second law, which can be seen below, applies here. The final velocity is equal to the initial velocity plus the net force times the change in time. In this lab, we applied this in conjunction with spring force, which can be written as the spring force is equal to negative k, which is the spring force constant, times s times L hat, which gives us our direction. We also solved for different types of energy, including potential and kinetic energies. Kinetic energy is given by 1/2 mass times velocity squared, and potential energy is given by mass times the acceleration due to gravity times the height. The initial conditions. The spring constant of our spring, as well as its relaxed length L0, were the same as those given in our edX videos, as the spring used was the same. However, the spring in the edX video only had a vertical component to its motion, while the video we analyzed had both a horizontal and vertical component. When we look at the code, we can see the things that we edited to create a system to model our experimental data. First, we had to set the mass equal to 0.402 kilograms given from the edX videos. This initial position was also given by the data in Tracker, as well as the ball starting from rest. Our time started at 0 using a delta t constant that we chose from our data. The force of gravity is given as 9.8 meters per second squared, and the spring constant from the edX videos was given as 6.83. Our relaxed length is 0.17 meters. In order to specify the vector L, we defined it as the ball's position minus the spring position of the spring. L hat, which gives us the direction, was L divided by the magnitude of L. And S, which gives us the compression or stretch of the spring, is the magnitude of L minus its initial length L0. Then, we saw 4 different types of energies. Kinetic energy is given as 1/2 times the ball's mass times the magnitude of the velocity squared. Potential energy is given as the mass times gravity times height. And the spring energy is given as 1/2 times the spring constant times s squared. The total energy is then given as kinetic plus potential plus spring. Here we had to calculate our vector forces. First, the force of gravity is given by the vector 0, negative m times 9.8, 0. The force of the spring is given by negative ks times s times L hat. The total net force is given as force of gravity plus the force of spring. Next, we apply the momentum principle, where we define the final velocity of the ball as equal to the initial velocity plus the net force divided by the ball's mass times delta t. The final position is given as the initial position plus the velocity times the change in time. Here we use the same formula that we used to update our spring as above. And finally, we calculate our changes in energy. The formulas for energy, kinetic, potential, and spring all remain the same, but for the changes in these energies, so delta K, delta UG, and delta US, it's simply the final minus the initial. And then the same thing for the total change in energy, it's just final minus initial. When we run our code and compare it to our initial model, we see several important things. First, the total energy given by this orange line here is 0, meaning that our energy principle is satisfied. Then we can see that in our exposition data, our experimental model, which is given in red here, started very close to our theoretical model, which is given in blue here. But as time increased, it moved further and further away. When we look at our y position data, we can see that it was very similar throughout the experiment. Assumptions. In this lab, we made several key assumptions that led to the discrepancies between our experimental and theoretical data. Firstly, we have to assume that our data in Tracker was calibrated correctly. Small mistakes in the placement of the origin or length of calibration stick could have made our data incorrect. Secondly, and most importantly, we had to assume that the spring itself had no mass. Real-world springs do have mass that affects them, but for the sake of this lab and most introphysics problems, we consider the mass of the spring to be negligible. What does this mean? When we looked at our graphs for energies, we saw that the total energy remained at zero throughout the experiment. Therefore, we know that the energy principle is satisfied because throughout all of the experiment, the spring energy, potential energy, and kinetic energy all summed to zero. Oscillations in the x and y directions. Using the data obtained in Tracker, make two separate estimates of oscillation periods, one from the x position data and one from the y position data. For both, we can look at our graphs in Tracker. The period for the x direction is given as 1.519 seconds, and the period for the y direction is given as 1.425 seconds. These are different for the reason that there are different forces in different directions. In the y direction, we have to account for both the force of gravity and the force of the spring, meaning it oscillates at a faster rate than in the x direction.